Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. Case in point, thank you so much for the follow. Really appreciate it. And yeah, what are we up to today? So let me go and open up CD projects, Swoleos. Also, let me know if there's an Let me know if there's a video audio desync or not. I don't think there is, but I didn't check today. I usually always check, and I just forgot to today. Swoleos, LS here. Let me do Julia double dash project. And let's go ahead and create. I'm just seeing it's a 3-minute wall sit. And here's the thing. I thought it was 55. I thought it was 55 rollouts. So I avoided doing the rollouts earlier today. But yeah. Okay. So the clap doesn't really help as much as you might think it would, because it's hard to find like the exact moment that a clap happens, you know? It's better just to look at the mouth and to see if it's synced up there or not. But trash talk, case in point, thank you guys so much for coming in. Let me go ahead and do using Swoleos over here. Create a superset, generate the next set, and we'll talk about what we're doing today. Thanks. Good. Appreciate that. So let's do superset is going to be equal to that. Let's cycle in the next set. And then, yeah, we'll just kind of hop into what we're doing today. It's not too different than the Sunday stream. Let me go ahead and do set. Here we go. So the next set is now leg lifts. Totally fine with that. 105 of them. That's a lot, but it's fine. I don't know why I have it set so high, but that's okay. Okay, so what I'm going to do, I don't know what I'm doing anymore. Let me just open up Zernal PP. Zernal PP. And we're going to talk about exactly what I mean when I ask the question, you know, what does it mean to be attracted to the Sierpinski triangle, right? That's the question of the day, nay, the question of the week. How do you know if you're attracted to an attractor? So let's start with how I got to this question, why we're changing, tact from what we did over on Sunday. So on Sunday, we asked the question, why, let me do this in text mode. It might be a little bit faster. Why are chaos games bad on GPUs, right? That was the question that we asked on Sunday, right? So the new question is, how do I know if I am attracted to the Sierpinski triangle? Okay, so now that's the new question. Okay, now looking at it, you might be wondering how these two guys are related, and they're actually incredibly related for a number of different reasons. Let me get a quick sip of water. Okay, so the first question over here, why are chaos games bad on GPUs, right? So as we were discussing why chaos games are bad on GPUs, we actually talked about a bunch of different solutions to this thing. We had this, the idea that we shuffle the array every time step, shuffle per time step, right? We also had the idea that we, how do I put this? We go through and we find some tricks to make it so we have a random variable stored in each thread, RND variable per thread. Now, the thing is, the way chaos games work is you take one value and you kind of iterate through at random which function you move to, right? So the obvious question comes up being that, we also had a third method dealing with tracking directions along a tree, right? So these are the three ways that we came up with to do it on the GPU. And the problem is all three of these ways are ways in which you can take a tree and essentially go through in a really shallow way, kind of like instead of going really, really deep into the tree and kind of going, okay, I'm doing a very good job of describing this. Here's the chaos game. We have 3 points, A, B, and C. A, B, and C, right? We have 3 functions. Function 1 is equal to whatever your point location is plus A over 2. Function 2 is going to be equal to point plus B over C. And function 3 is going to be equal to point plus C over 2. I just suck today. 1 second. Let me try this again. So the idea is that each of these functions will bring you halfway towards A, B, or C, right? So if we have a random point in space, let's say this one, we choose at random one of these functions. So it moves halfway towards A, and then halfway towards B, and then halfway towards C, and then halfway towards C again, then, I don't know, halfway towards A. And eventually by picking these points at random, you will eventually create the Sierpinski triangle, right? So eventually you'll create the very well-known triangle of triangles, right? In here. And this is kind of how the chaos game works. You pick one point and you just kind of randomly choose functions at every step. So for example, we take a point and, there are 3 possible options. And from this point, there are 3 possible options. From this point, so on and so forth. There's always 3 options from each of these guys. I'm just going to draw the next layer, but after that, you know how it goes. I'm just going to do ... in here. So for example, we might choose to, function 1 at the start, function 2, then function 2 again, then function 1, then function 3, then function 2, then function 1, so on and so forth. So you are eventually just going down this tree very, very deep. Now, the GPU obviously works in parallel, and it doesn't do very well with iterative things. So in general, you're not really going to be, you're trading, going down the tree very, in an incredibly deep fashion, function after function after function, with a bunch of shallow dives into the tree. And sure, you can do some iteration, but the power of the GPU comes from doing many trees in parallel, not doing one tree very deep. And so my question came about, from this discussion, what actually is the better way to do a chaos game? Is it better to, choose as many functions as you can in an iterative fashion, or is it better to do it in parallel? So then the question is, how do you know how far away you are from the Sierpinski triangle? Is this green point on the Sierpinski triangle, or is it slightly off of it? What is the distance measure between a point location and the triangle it's supposed to be on? More than that, how do you know you're next to any arbitrary attractor, right? How do you know that this function system is going to give you this attractor, right? And in this linguistics, the way that we're talking about this is, this over here is your function system, and this is your attractor. So the very obvious question is, or the set of questions that are all kind of related here are, one, how do you know that your function system has a particular attractor? So how do you relate? How is the attractor related to, and this is my little related to symbol, your function system, right? How do you know you're attracted to the Sierpinski triangle and not some other system, right? And 2, how do you know how close you are? Like, what is your closeness metric to your attractor, right? Attractor. So these are the questions that I want to solve here. How do you know what function system will give you what attractor without just knowing? Like, for example, we know that this set of functions creates a Sierpinski triangle, but we know that because we've done it a lot of times. Now, how do we know that some distribution of points is arbitrarily close to the Sierpinski triangle? That's the next question. And so these are the questions that I'm trying to solve. And in principle, it makes sense to do this now instead of doing it next week. We could continue hammering out the GPU stuff, and I think we will do that next week. But we kind of, in my mind, need to figure out, how do we even measure, like, whether a method is more or less successful than another method? Because if we want to try, method 1, 2, and 3 in here, well, we kind of need to know which one's working best, We can visually by eye say that, the Sierpinski, this one looks more triangle-esque, triangle-ish, and that's totally fine. But how do we know that, for example, this method in here, provides a better triangle than, for example, this method in here, There's obviously time, but time to what? We need some sort of metric, time to, being 0.01, away from the Surfancy triangle, 0.01 in what metric? So that is the question that we're trying to solve here. How do we know if we're being attracted to the Surfancy triangle or some other metric? So that's the question. Let me get some water. And yeah. I think to hop into this, the first thing we're going to do is just kind of look into attractors and see what we can find. That is Twitter, attractors. And just kind of look into it, see what we can do. I don't know attractors as well as I should. All I know them as are, if you have a function system, all I know is that the attractor is an output to a function system. That's all I know. I'm hoping to learn a bit more here. And hopefully that will give me some intuition as to distance metrics from attractors, I think is what I should be looking for. Distance metrics from attractors. And we'll just see what we can find, you know? Metric for attractor overlap, attractor radius, and global attractor radius. Maybe this is what I'm looking for. Let's see. Let me go put this on Google instead of DuckDuckGo. And again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know, and I will totally address it as soon as I see it in a chat. Took me one finger to pop open a Dr. Pepper can. How else do you open up cans? I'm sorry, like, do you like use like a claw? Like, just open it up like that? Anyway, this is where we're at. So, detecting changes in force, analysis of attractor distances, and random Boolean networks. Maybe this is what we're looking for. But yeah, so metric for attractor overlap maybe this is what we want. But yeah, let's just read up on the attractor. Make sure that this is the same as an attractor for an iterated function system. So also at the same time, I'm going to look up iterated function system on Wikipedia, because it does mention stuff about attractors there. So let's see. Let's go here to Attractor. Okay, right. So recently it was shown that iterated function systems of non-contractive type, i.e. composed of maps that are not contractions with respect to any topologically equivalent metric x, can yield attractors. Okay, let's move down here. These arise naturally in projective spaces, though classical irrational rotation on the circle can be adapted too. Okay, so that didn't help me, as you might imagine. Let's keep going. That's the only variation of attractor here. So let me see if I can find a bit more information here. Chaos games, games and attractors. Let's see, chaos game. So in mathematics, the term chaos game originally referred to a method of creating a fractal using a polygon and an initial point selected at random inside of it. The fractal is created by iteratively creating a sequence of points starting with the initial random point, in which each point in the sequence is a given fraction of the distance between the previous point and one of the vertices of the polygon. I'm looking specifically for attractor in this Okay, the term has been generalized to refer to a method of generating the attractor or fixed point, or the fixed point of any iterated function system. So what is a fixed point? I'm sorry, guys, we're going real deep into this. In mathematics, a fixed point, sometimes called sometimes shortened to fixed point, also known as an invariant point of a function, is an element of the function's domain that is mapped to itself by the function. Okay, so in the case of the Sierpinski triangle, obviously the function system will create the Sierpinski triangle. Therefore, it is the function's domain that is mapped to itself by the functions, plural. I do get that. But let's dig a bit deeper in here. So we say y is equal to f of x. So a point with 3 fixed points. A function with 3 fixed points. So why are they the fixed points? So in mathematics, a fixed point of a function is an element of the function's domain that is mapped to itself by the function. That is to say, c is a fixed point of the function if f of c is equal to c. That means, okay, I kind of see what it's saying. So it's saying, like, for example, if you have the function f of x is equal to x, then the entirety of that domain is a fixed point, because, you know, at every location when you put the value x into the formula, you're going to get back out x. So journal, new page before. If, for example, you have, let's do that little siny boy that we saw a while ago. It kind of goes like this, something like that. So, for example, if this here is 1, 1, then it would have a fixed point because f of 1 is going to be equal to 1, right? And let's say this down here is, I don't know, -1, -1, then f of -1 is also a fixed point because it returns -1. Okay. Now the question is, how is that related to attractors? And not sure. So maybe what they're saying is that the iterative function system might not have an attractor, but instead has a fixed point, which is, like, maybe that's the difference. Like, an attractor is a specific shape, whereas a fixed point is any, like, output of an iterative function system. So let's go here to fixed point. Okay, so examples. The diagram shows the construction of an iterative function system from 2 affine functions. Okay, the functions are represented by their effect on the bi-unit square. The combination of two functions forms the Hutchinson operator. 3 iterations of the operator are shown. Then the final image is of the fixed point, the final fractal. Right, final fractal. Okay, right. So if the attractor, basically the fixed point is the end result of an iterated function system. An attractor is a potential fixed point, but not always the fixed point. Okay, so now the question is what is an attractor, and in what situations does an iterated function system give you an attractor versus a fixed point? That's the question, and I don't actually know in this case like what makes an attractor and what makes a fixed point. So let me see, is the Sierpinski triangle an attractor? Sierpinski attractor. That's my question. Surfancy Attractor, if you don't know the game, see its description in the pages. I'm assuming... Yeah. What do we have here? This does not fit my browser at all. Okay, but my assumption here is that this is considered an attractor. My question is, why is the Sierpinski triangle an attractor? Instead of, like, for example, this guy, why is this guy not an attractor? But instead a fixed point. Okay, so let's see what we can find here. Go back a bit. Surfancy triangle. So let's just look for the word attractor here. Is a fractal attractive fixed set. Okay. You bring me back to a fixed point, but attracting fixed points. Okay, yeah, maybe this is what I want. So an attracting fixed point of a function f is a fixed point x naught of f. I think we already have this up earlier, fixed point here in a bigger font. So let's just take a look. Okay, one more time. Scroll down here. So attracting fixed point, I think that's where we need. Look at Wolfram Rule 90 and the Apollonian. Let's see, Wolfram Rule 90. What do we have here? Rule 90 is one of the elementary cellular automation. I don't see how this helps exactly. I don't really want to deal with cellular automata. Yeah, I mean, yeah, okay. And then you said the next one is the Apollonian. Apollonian. I misspelled it, but I'm sure it'll find it. Sure. Yeah, let's search for that. Nope, no. This is what I want. And then we look for... How does this help? Let me see. Let me do this on Google. There. Apollonian gasket probably is what we're looking for. Right, this is probably what we're looking for. Is a fractal generator starting... Right, this... I'm gonna go back to the fixed point. Okay, so an attracting fixed point is the same as a triangle. Fair enough, yeah. So an attracting fixed point of function f is a fixed point x naught of f, such that for any value of x in the domain that is close enough to x, the iterated function sequence converges to x. Okay, I got it. So basically, the fact that we can... Okay, this is telling me that... what do we have here? Essentially, if the function system creates a shape, you can basically say that that shape is the iterated function system result, right? So this is... Because this is the act of doing an iterated function system. It's just apply the function to another function to another function, right? So the reason the iterated function system works is simply because of this feature that the Sierpinski triangle is basically an attractive fixed set, or an attractive fixed result, right? So that makes sense to me. We might have to edit the iterative function system chapter in the algorithm archive to reflect that, which is totally fine. And yeah, so now my next question is, can you tell from the set of functions itself what the attractor will be, right? Like, can you tell from, the point plus a over 2, point plus b over 2, point plus c over 2, can you tell that that's going to give you the Sierpinski triangle? And I have no idea. I have no idea whatsoever. So let's see, starting with any X, no, this is just a description of the chaos game. Okay, so let's take a look at the Attractor then again. And yeah, let's just see what we can dig up here. So in the mathematical field of dynamical systems, an attractor is a set of numerical values towards which a system tends to evolve. Again, with the iterated function system, you tend to iterate onto the Sierpinski triangle. Therefore, it is, in general, I think, can be considered to be an attractor. I don't really know the distinction here between a fixed set and an attractor, but I think it'll describe that down here. Fixed point is a type of attractor. Okay, perfect. Right. So in that case, then basically any iterated function system will have a fixed point that it goes to. Therefore, they all have attractors, so I think that's totally fine. Okay, so the next question I have is, how do you tell the fixed point of an iterated function system without iterating? I guess my point is I want to find an error metric to the iterated function system. So let me see if I can just Google error term to iterated function system. It might actually be in here. Yeah, let's see if we can just find errors in here. Error. No. It doesn't talk about error at all, which I guess is fine. Okay. The inverse problem, very fast algorithms exist to generate an image from a set of iterated function systems, or PIFS, which I don't remember what it stands for. It is faster and requires much less storage space to store a description of how it was created, transmit that description to a destination device, and regenerate that image anew on the destination device, than to store and transmit the color of each pixel on the image. Right. So that was what I was kind of afraid of, because the iterated function systems seem to return back an image, right? You're basically saying, how close is the image that you're generating to, the Sierpinski triangle, to the result that you've gotten from the iterated function system. But I think potentially this is what we want. So the inverse problem is more difficult. Given some original arbitrary digital image, such as a digital photograph, try to find a set of iterated function system parameters which, when evaluated by iteration, produces another image visually similar to the original. In 1989, Arnold Jacquin presented a solution to a restricted form of the inverse problem using I don't remember what the P stands for. We just looked at this on Sunday, but it's something iterated function system. The general form of the inverse problem remains unsolved. Right. So as of 1995, all fractal compression software is based on Jacques' approach. So this brings up an interesting point then, right? So what we're looking at here is we're looking at a system where we know how to go from an iterated function system to an attractor, right? This is easy. You just iterate. So then the next question is, how do we go from an attractor to an iterated function system? Can you please explain why you're interested in this question in the first place? It's not about whether, so like we said before, on Sunday we had this huge, I spent like 30 minutes talking about it, but that's okay. So on Sunday we had this discussion about why chaos games are bad on GPUs, right? And we talked about how iterated systems on GPUs are they just don't work very well. So we came up with 3 potential solutions. And the question is, first of all, which one can give you the Sierpinski triangle in the shortest amount of time? But in order to determine that, we need some sort of metric to see how close the representation is to the Sierpinski triangle, right? Like, are we 50% there? Are we 100% there? Are we off by 0.01? Off of what by 0.01? We need some sort of metric to see how close we are to an arbitrary attractor. Not just the Sierpinski triangle, but the Sierpinski triangle is an obvious one to start with, right? So once we can find that metric of how close we are to the Sierpinski triangle, we can then return to the question of how do we appropriately compute it on a GPU. But the question of how close we are matters a lot when we're talking about other fractal systems, like, for example, the fractal flame method, which has a whole bunch of different affine transformations kind of squished together. So then the question is, hey, are we actually, representing the system appropriately? Will this particular affine transformation need longer to generate than another system in the fractal flame method? Like, these questions are ones that you need to be able to answer. And quite frankly, I don't have a solution to any of them. And like we just saw, which makes it even more interesting, we know that this problem, going from an iterative function system to an attractor, is actually it's an easy problem, easy peasy, right? But this guy, the attractor to the iterative function system, is now an inverse problem and also unsolved, right? And so because it's an inverse problem that is unsolved, it's now actually a very interesting question that's apparently very, very close to fractal compression, which is exactly what we talked about on Sunday. So this question of, how do you know if you're attracted to a Sierpinski triangle or some other attractor is exactly the same question that we were asking on Sunday on, how exactly do you compress an image into a set of equations, such as an iterative function system, to basically allow you to, ensure that you will always move to that attracted result. You know what I mean? So this is why it's interesting, right? The question is, essentially, the end result is, after maybe 6 or so weeks, the end result will be, how do we basically turn any image into a set of equations? That's the end result, and that set of equations will also be a set of fractal flames. That's the end result that we're looking for. Right now, we're at the stage where we just need an error metric, and so that's exactly what we're solving right now. How do you know if you're attracted to the Sierpinski triangle or something else? Also, I do apologize. I know I sounded a bit rambly there. Yeah, I definitely apologize for that. I did not mean to sound rambly. I just sometimes sound that way when I get kind of in the middle of excited and talky, Okay, so this is actually really cool. I'm psyched about this. Now that we know this is the case, let's kind of spitball some stuff here. So this means right. What I was trying to ask at the start of stream was the following. Again, how do you know if you're attracted to the Sierpinski triangle? And this comes up with 2 additional questions. How do we know that how do we know what attractor is related to a set of function systems without iterating through the set of function systems? That's question 1. And question 2 is, do we have a closest metric to the attractor? Now, like we saw, the attractor can be a bunch of different things. It could be the Sierpinski triangle, which is a triangle of triangles, or it could be a number of other things that aren't necessarily, so defined. Like, for example, this image in here is also an attractor, right? But, performing a closeness metric for this guy is remarkably different than performing a closeness metric for the Sierpinski triangle, right? Because you can imagine if you have some point in space like this guy over here, you could define a distance from the Sierpinski triangle as, your closest metric, which I guess I'll call alpha here. And I suppose you could do the same thing here you could do the same thing here. But it just kind of leads to a lot of questions as to, with the Sierpinski triangle, I can imagine that there's an analytical form for it. With something like this, the analytical form must be the function system, right? No, the function system is the analytical form. Okay, now I'm just getting confused, right? So what I was ideally looking for was some sort of analytical form to this triangle, right? That's what I'm looking for. With the assumption that any iterative function system has some sort of analytical form that can eventually allow us to find the closest metric, closeness. That's what I'm looking for. Again, some sort of analytical form that allows for us to find that closest metric. So let's just look at analytical form for Sierpinski. Let's just see what we can find. I mean, we know it's a bunch of lines, right? So Chaos Game, it doesn't look like, and this is actually exciting in a way, it doesn't look like, it doesn't look like there is, in fact, a clear analytical description for what the Sierpinski triangle is, which is great, actually, because that means the problem's more interesting than we thought it was, right? Like, anytime I find this stuff where it's like, the solution is not obvious, right? Like, sometimes when you're looking for things and you find an obvious solution, it's like, okay. Right, that's what I think as well, Steve. I think that the analytical form is literally iterative function system plus a starting point that's on the attractor. I think that's what it is. And you just happen to know what the attractor is because you know what the Sierpinski triangle is, right? Which is interesting in and of itself, because that means the closeness metric must... Oof, that's a tough one. That's a really tough one, right? Because, for example, I'm going to take a little square here, like maybe a square right there, where those points line up. If you look at it from a distance, what it's going to look like, again, I'm just going to make the square really big here, is it's going to look like... that was not what I meant to do. It's going to look like maybe the edge of the triangle goes along here. Let's maybe make it go along there. Perfect. And then you see part of the triangle come up, and then part of the triangle come back down, right? So this is like, I kind of blew up the section to look something like this. But that's not really what it is, right? An iterative function system, with an iterative function system, the lines are kind of a lie, right? The lines are a trick that your eyes play on you because there's so many points generated, right? What actually this is a bunch of points that are... Actually, I know that is a point. There's a point here, and then there's like points that lead up here, and points that lead down here, and points that lead over here. So if you have an arbitrary point, let's draw it in pink over here. Well, actually, let's draw it right there. Now the question is a bit trickier, right? The question isn't how far away are you from this line. The question is either how far away are you from either of these points, which are the closest you can find to the iterative function system, or maybe you find some interpolation between these points, and that interpolation is now the line that you find the closest to, right? So if the analytical form is the iterative function system, then we run into the issue that the iterative function system is actually a set of points, not a line, and then we ask the question, hey, how do we know how close we are to 1? How close... I'm going to draw this little DNA symbol for our closest metric. A collection of points, which is definitely something you can do. Points. Or 2, an interpolated line. Okay, so those are kind of, this is where my mind's going right now. And again, guys, if you have further ideas, concepts, like things that you want to throw at me, feel free to do so. I've got a feeling that we're going to jump back into fractal compression in just a bit, because it seems to me like I want to learn more about this inverse problem. It also doesn't help that your end goal is to compress data images, and images don't have infinite resolution, but are made up of pixels. Right, that's another issue that we can kind of, I think, table for now, but come back to it in a bit. Because again, what we're looking for, so what kind of bugged me, I don't know who was here on Sunday, but what really bugged me about Sunday was the following. So fractal compression, I'm just gonna fractal compression. Okay, so the way this works, the fractal compression method, is you start with some sort of image, right? And we don't really know what the image resolution is to start, but we assume that the image resolution is high. What you then do is you find an iterative function system of this image. So you turn the image into an iterative function system. Then what you do is you store a low quality version of the image. So let me just do, I'm just going to say, how am I going to do this? I'm going to put another image over here. I'm just going to write on these guys. So this is high quality. This is low quality. And this is a high quality, but I'm going to put a hat on it, right? So what you'll do is you'll take the high quality input image. You create an iterative function system, which essentially gives you a fixed point, an attractor that is the image back out. And then you save a low quality image, feed it through the inverse function system to get this high quality image out. Now the high quality image will of course be compressed, it's lossy, there is some information missed. That's why I put a little hat on it. But in the end, what you're looking at here is a high quality image saved as a set of functions, and then you store some sort of low quality image to pass through that set of functions. But what bugged me is that if this iterative function system is in fact, or if the attractor of the iterative function system is in fact the high quality image that we started with, right? If that's what it is, then we shouldn't need to store the low quality image at all, because in principle, any arbitrary set of points should return back the high quality image after some iteration, right? So that says to me that the iterative function system that we have here, the true attractor is not actually the high quality image. The true attractor is only the high quality image with some particular input. And so that was what bugged me about Sunday. And I spent some time thinking about it again and trying to figure out exactly how to frame this question, which I still don't know. But I'm more than happy to look more into the fractal compression just discussion, because not only did we find that it's basically an unsolved area where, like, an unsolved inverse problem, which makes it interesting in its own right, but we've also discovered that there are ways to improve this already. Like if, for example, the iterative function system was just closer to the original image, or its attractor was closer to the original image, then we could store either an even lower quality image, or potentially, and what I'm hoping for, no image at all, and literally just iterate on a set of points and bin those points. So that's what I'm hoping for, not to have to store an image and only be able to store the iterative function system. Now, for obvious reasons, clearly this is not, like, I'm probably shooting for the stars here, but that would be really cool, wouldn't it? If we could represent any high quality image as a set of functions. That's the coolest result you could possibly imagine there. I mean, like, sure, maybe there are cooler results, but yeah. Okay, so let's go back to talking about the Sierpinski triangle itself, and go from there. IFS may in general have multiple attractors, like any dynamic system, I believe. That's why you need just for a low starting point. You're right. Maybe that is it. Maybe in general, but not all function systems. In fact, most function systems only have one attractor. Isn't that right? I thought that most function systems that use via the chaos game only have one attractor. But I suppose you're probably right in that some iterative function systems that are used outside of that framework probably do have multiple attractors, right? So then the question becomes, how do you specify what attractor? Like, can you take a system that has two attractors and, like, make it one that only has one attractor without giving it an initial, like, set of points, Make some water. Anyway, the point is that there's a lot of interesting questions here that, I never really had time to solve during the PhD or during the postdoc, but kind of came up a long time ago when we were doing fractal flame method for the first time. And I'm just quite interested to see if maybe, delving into them here gives us any sort of result. If not, we're definitely learning something, and that is something there in and of itself, Okay, let's go up to the top here, and let's just read a little bit about it, just to make sure that we're not being dumb. List of fractals by Hausdorff dimension. That might also be something. But yeah, in general, like, I know the question's a bit weird, but it is a question that it's a legitimate question that I'm trying to answer. As to tell, like, obviously the Sierpinski triangle is an attractor. The question is to see, if we're starting to generate a bit of points, maybe how many points do we have to generate via the chaos game to know that the attractor is the Sierpinski triangle? Maybe, how far away are our points from the Sierpinski triangle as I start iterating through? Does the error actually matter? Probably not, in which case, maybe what we can do is we can just generate a high quality iterative function system via the CPU, and then we just find, how far away we are from that collection of points after doing the GPU iteration. The only thing I'm really worried about with the CPU GPU split is, again, that the GPU, I know that after like 20 or so iterations on the CPU, we will eventually hit something that's close enough to the Sierpinski triangle that no one's really going to know the difference. But with the GPU, I'm, let's say we have a different system that's not the Sierpinski triangle. Let's say we have a system that is, again, like maybe one of the fractal flame methods that is like some sort of weird heart thing, I feel like we have to throw away more iterations on that, and I don't know the number of iterations we have to throw away to do something that's more complicated, right? So no matter what the case is, having some sort of closest metric, I think, is really important. Even if it ends up going nowhere, like just asking the question, I think, is worth asking. So I think we actually might want to do an error metric on this, head-on map or something like that. Something that's kind of like a simple 2D attractor that's not like a bunch of lines, But anyway, let's just kind of, let's see what we got here. Okay. Back to the Sierpinski triangle, go to the top here. And then I think we're gonna, you know, kind of find some articles to look at for next hour, which will probably be related to fractal compression and stuff. So that's where we're at. I'm not sure how long I'm going to be streaming today because of a few reasons. One, I definitely have to drop off at 6. 6 is the latest I can go. I realize it's 3 o'clock in the afternoon my time. But the other thing too is I might just end up having to read a lot of papers for this, which is totally fine. Like I'm really happy to read a bunch of papers. But the question becomes, can I or should I read the papers on stream, or should I save stream specifically for programming? And so what we might do is we might queue up a bunch of papers, kind of start going through them, you know, picking them apart, seeing what we actually need to do. And then we might just, or I might just go and read them and try to figure it out on my own. We'll see how that goes. Adding the push-up, thank you for that. Okay. So yeah, let's read a bit about the Sierpinski triangle and go from there. So the Sierpinski triangle, sometimes spelled Sierpinski, which is the same, I think, just without the dash on the end. Also called the Sierpinski gasket or Sierpinski sieve, is a fractal attractive set with the overall shape of an equilateral triangle subdivided recursively into smaller triangles. Originally constructed as a curve, this is one of the basic examples of self-similar sets. That is, it is a mathematically generated pattern that is reproducible at any magnification or reduction. It's named after the Polish mathematician Wacław Sierpinski, but appeared as a decorative pattern many centuries before the work of Sierpinski. Hey Chester, how are you? Things are going okay, thanks for asking. What do we have here? There are many different ways of constructing the triangle. Obviously, the evolution, yeah, that's fine as well. What is interesting though is this does kind of solve or start showing the problem that I was discussing earlier. Increased difficulty of next set. Yeah, I'll do that. So we should just do set is equal to increased difficulty. And that should be, I don't know how many we have to do now, probably 135, I'm gonna guess. 124 legless for the next. We're gonna do it in about 10 minutes, so feel free to join if you want. But yeah, this guy here does show the actual problem in that, right, so if we only do shallow dives into the tree that is the iterated function system, we are missing out on some resolution, right? That is to say, like, maybe that is the solution. Maybe specifically for the Sierpinski triangle system, or the Sierpinski triangle iterated function system, I reckon that at any point in time, no matter what point you arbitrarily choose, no matter if that point is on the triangle or not, you can be at most the distance of one of these triangles away from the Sierpinski gasket. That's my conjecture. That's what I'm gonna try to figure out. So for example, if your point's all the way over here, well, that's not true. You could select your point all the way over here, in which case, yeah, never mind. I've already disproven myself. Dang it, I was hoping. Okay. But what this is kind of telling me is that there doesn't seem to be a general analytical form for the lines that are on the Sierpinski triangle, which is, again, what I was looking for. But, you know, if I don't find it, it's totally fine. Okay. Then, in that case, the usage of the word gasket refers to the Sierpinski triangle. To refer to the Sierpinski triangle refers to gaskets such as are found in motors, which sometimes feature a series of holes of decreasing size, similar to the fractal. This usage was coined by Mandelbrot, who thought the fractal looked similar to the parts that prevent leaks in motors. Okay. And then, of course, we have Sierpinski gasket. Now, that... Oh, okay, it's just a square version of Sierpinski gasket. Fair enough. Let's remove that. Let's see. I didn't find anything here. But maybe we can find something later. Again, the question of how far off are we from an attractor is the question we're trying to solve. I'm going to remove these guys for now. Chaos game, again, that didn't give us what we needed. Golden square fractal, I think this might be the right page. Yes, this is what I'm looking for. So I'm going to look for 7, 8, and 5. Here we are. 7... 8 and 5. Sure, yeah, let's take it. Yep, why not? And it is, okay. Algorithm for fast fractal compression. Which ones did I grab? I did 7, a review of fractal image compression literature. Algorithm for fast fractal image compression. And then the last one was fractal image compression, which I think we looked at before. In fact, I think MQ we've definitely looked at before. Fractal image compression. Yeah, we had this yesterday. I just didn't look at it because it was old. Right. Thank you so much for the bit, Anonymous Tier. I hope you're having a wonderful day. Okay, so let's just make sure these are in the appropriate directory, and we can kind of look through them, see what we can do. Okay, so yeah, we'll just see how this goes. I'm actually happy to see Lena in there. This one we also did not read. Okay, perfect. So let's just grab both those guys. I think if I just go to downloads, I think that, oh, okay, download here. Oh, I just downloaded the page. That wasn't what I meant. 1 second. Download open. Okay. I don't know how to find which things I just downloaded, if I'm being honest. Okay. Well, I can just click on this button. MQ. Okay, so we don't want to download that one, but we know where it is. CD projects. Flamify. CD notes, ls here, and let's just go ahead and move this guy, and it's gonna be MQ download, sorry, MQ, move that here, and now we're just not gonna download this guy this time. Okay, the other one we wanted was this guy, which is okay, there. I guess I don't have access to that one, and then the other one was 7, which was SAHA. Okay. 1 second. CD projects, Flamify, CD notes, move, downloads, SAHA here. Okay, so we got a few more things to read. I'm gonna check to see if maybe there's a way to get this guy. In fact, we might already have this guy. Highly influential citation. Huh. Okay. Well, anyway, it doesn't matter. Go back here. And let's just see if we can find this. So it says view on SPIE, but I don't think that's open. I think we're going to have to find it some other way. What was the paper you didn't have access to? I'm looking at it right now to see if I can find access to it. Let's see. I'm just going to grab this guy, and I'm just going to go to Google Scholar and see what we can find. Algorithm for, yep, so we can just find it here. Perfect. And it's 296.pdf. CD projects, Flamify, oh, let's here. Move, downloads, 296. Put it there. Okay, perfect. So we have everything that we need. We're going to go ahead and do the 5-minute workout for this hour, and then we're going to move on to reading those papers and see what we can find. But yeah, that's good. So we have everything that we need. And we're just going to take a look at those papers at the top of the hour once we finish up everything else. Again, we are going back to the fractal image compression with the hopes that this gives us some information about the inverse problem that we're trying to solve here. Again, with the hope that this helps us. Yeah, again, we're looking for a distance metric to an attractor right now. That is exactly what we're looking for. But we'll see if this allows us to maybe hone in on the problem a bit deeper, you know? Okay. So again, I will be right back. I'm going to change scenes to the workout scene. We have 124 leg lifts to do, along with 4 push-ups. So we'll go ahead and do that in the next 5-10 minutes. For those of you guys who maybe have not been here before, we, at least for the past few months or past few weeks, have been splitting up 5 push-ups to do. That's totally fine. We've been splitting up what we do here on stream to basically be 55 minutes of some sort of project, and then 5 minutes of exercise. And the hope is that, you know, people join along at home. They don't have to do the exercises if they don't want to, but just kind of get up, do some sort of movement just to get their blood flowing a little bit. Again, just to kind of break up the monotony of the day and just kind of reinvigorate us, you, whatever, so that we can keep working at a bit of a faster pace than I normally would. At least for me, it's massively beneficial. For other people, it's maybe a 5-minute break off the stream every hour or something, and so I think that's totally fine. Okay, so let's just open up some additional music in here. I will go to chill EDM like normal. Go ahead and turn this off, turn that on. It is playing. And I will be right back as I change the microphone positions. So give me just a minute here. And yeah, then we'll do the leg list and everything else. Okay. Oh, I need to bring down Twitch chat. Give me just a second. 1 second. And then we can start. What do I have here? I think I need to do this. And that. You can say anything? No, you did not. Perfect. Oh, actually, that doesn't help me at all. Oh, no, how do I get to my profile? This is probably fine, but I was hoping for... Oh, now I can hear myself. Shoot, how do I just cannot work this app to save my life. Probably because I'm never on this app. 1 second, let's go there. There should be channel... Stream manager. There we go. Perfect. Okay, so now I have everything set up. Again, it's 5 push-ups and then 125 leg lifts. So let's go ahead and get started. Oh, you guys should be able to hear me just fine. And yeah. Okay. 1, 2, 3, 4, and 5. Okay, so 124 leg lifts are kind of weird. So how do we split that into a set of 3? I usually split it into sets of 3. That would be 90s 30. So then we have 60 more than that. No, we have 30 more than that, so 33 more than that. So that's going to be a set of 43. So it's 43, 44, 43, I think is what it is. Is that right? 44, 80... Wait a minute, I need to think about this. 88 plus 20, 88 plus 44 gives you what? That gives you 128, 132. I'm way off. 41, 42, 41. Yes, that'll work. Yeah, that'll do. Okay, so what I'm actually gonna do then is I'm gonna do a set of 40, then 44, and then another set of 40. So that means I'll do 20 up, and then 20 on the left and 20 on the right. And so it's just gonna be normal leg lifts. Again, if you guys want to join from home, feel free to do so. It's just a set of leg lifts just to kind of get the blood flowing and start the next hour in good spirits and everything. So let's go ahead and get started. I won't have a timer for this one. We'll just kind of go. It should just be 40 up, and then 20 on one side, 20 on the other side. So, or 10 on each side. All right. So if anyone's joining from home, we're gonna start in 3, 2, 1, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. All right, side to side. So I'm gonna do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. All right, that's 1 of 3 done. Now we just have 2 more to do. So the next one's gonna be set of 44. So again, I think I'm gonna do, how do I wanna do this one? I'm gonna do, let's do 22 up and then 21 on either side. And so that'll be a set of 44. And we might as well just go ahead and get started. Leg lifts are one of those things that don't really, like, I feel like they should work more than they do. Sorry, I know I have one of my friends, like, leg lifts are like his least favorite leg exercise. But for me, it's like, it's fine. I've never really struggled with them before. Okay, let's start on the next set. So again, it's gonna be 21 forward, and then, no, 22 up, and then 21 on either side. So that's a total of, 1 second. Yeah, that's right. So 22 and then 22 again. Yep, that's what I want. Perfect. All right. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20, 21, and 22. All right, side to side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22. Okay, one last set, and then we'll get back to programming. I'm gonna take a quick 10-second break. Again, if you guys are doing from home, you guys don't have to do, you know, however many 124 leg lifts. Just do however many you feel like. Even then, you don't have to do any at all if you don't want to. Just kind of get up, get the blood flowing, get ready for the next hour, that type of thing. We are actually a little bit over the 5 minutes, but that's okay. Okay, last set of 20. Wait, of 20 and then 20 on each side, or 10 on each side. Okay, and I'm gonna go in 3, 2, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. All right, perfect. All right, let me go ahead and change the microphone position. We'll get back to the regularly scheduled programming. And actually, guys, give me just 1 minute. I'll be right back. Okay, I'm back. Give me just a second, guys, to reset up. And yeah. 1 second. All right, should be good. Okay, so one thing to start, or to do before the next set, let me go ahead and cycle set. We have to do 110 push-ups. Who came up with that one? What? 110? Can I even do 110 push-ups? Okay, well, we'll see how that goes. With the normal push-up counter, I don't know why I thought that was a good idea. Okay, so what we're going to do is we're going to CD into projects, Flamify over here, LS here. CD into notes, and we should have a bunch of PDFs that we just created. I'm just going to open them up and see which one we want to tackle first, just by reading the abstracts, and see where we go. I did the make more difficult, but that's a rough one. No, it's okay. It only makes the next set more difficult. Let me go ahead and set that to 0, and then we're going to, we should have a push-up counter of 0, and also let me make it so the push-ups are actually on page. Okay, so let's just take a look at these guys. I'm just going to, let's just Ocular start up PDF. All right, we're just gonna open them all up and see what we got here. So, review of fractal image compression literature. This is just a discussion of fractal image compression. It's a review, which is quite nice. So I kind of feel like maybe we should tackle that one first. This one is, I believe, a survey on parallel algorithms. We'll talk about that later, probably next week or the week after. Fractal image compression by LaCroix. I mean, the guy's famous for his bubbly water, so maybe that's useful. Let's see, what do we have here? I've got a feeling we still want to do the review, but this one looks promising. Let's see. Next one, Fractal Image Compression by Barnsley. We read that one on Sunday. And then this one is, oh, this is the one from like 1991, and like, it didn't look promising. So, okay, it is between the review and the survey. So the review is a total of how many pages long? It looks like it is, let's go to view. Oh, yeah, I don't know, view mode, overview. It is, I don't know, how many is that? 9 pages long? No, not even. It's 1, 2, 3, 4, 5, 6 pages long. And this guy over here is view, view mode, overview, view mode. Oh. Facing pages. Okay, how many is this? This is gonna be. Oh, it says right there. So it's 61 pages. I think maybe if we're gonna read something on stream, let's read the other one. Because I don't want to go through 61 pages on stream. I might do it off the stream, but definitely not on stream. Okay, so let's just go through this guy then. View mode, and we're gonna do single page. I'm going to make it so we can read both at the same time. In fact, let's just go over here and let's just do Zernal PP. I think that was Saha, I believe. Yeah, review of image compression literature. So we'll just have this open and we're just going to read through it and see what we understand. So again, guys, where this fits into the general scope, we're still looking for the question of how do we tell whether a point is attracted to the Sierpinski triangle or some other attractor. That's still the question that we're trying to solve. What this gives us an idea of is kind of the opposite question of, you know, if we're given the Sierpinski triangle, how do we know what specific iterated function system set comprises that fractal, right? And this allows us to potentially start asking the question of different distance metrics and stuff like that. So yeah, otherwise we can find an error based on allowing one Sierpinski triangle to evolve sufficiently long so that it's basically done, and then we can find a distance metric from the nearest point in some sort of like other way. Like, again, it's just gonna be a set of points. So we have some sort of point cloud, and we're just finding the distances between like one point and a point cloud is definitely something that people have done. Web BSK, thank you so much for following, really appreciate it. Okay, so review of image compression literature, fractal image compression literature. It's still a bit long, but I think going through it on stream here is gonna be beneficial. And yeah, again, like I said before, if it feels like we're just kind of swamped, and we are going to be doing a lot of reading of different papers and stuff, stream might be short. I might end on the next hour. But if we kind of feel like you know, we're making headway and we have an idea of where to go from there, I might continue. So this is kind of, I'm not sure how much longer the stream will go. It might only go for another hour, or maybe till the top of the hour, so maybe another 45 minutes, or it could go significantly longer, just depending. I'm just giving everyone a heads up there. So, since the conception of fractal image compression by Michael F. Barnsley around 1987, let me go ahead and draw this. The research literature on this topic has experienced a rapid growth. Following is a brief description of the major advances in the field and the largest comprehensive bibliography published on this topic to date. This is published in 1994. So only like, what is it? What's 4 minus 7? That is 7. So it's only 7 years after Barnsley originally proposed it. So this says two things. One, it says that the field actually didn't evolve much after this stage, which is important. It's important to make that note, that other image compression methods beat this one out pretty soon after this fact. But on the other hand, it's interesting because it means that people were significantly interested in this at some time, which is another thing that, again, maybe we should keep in mind, you know, as we go a little bit further here. Okay, Control Z a few times. Okay. Following is a brief description of the major advances in the field and the largest comprehensive bibliography. While JPEG is becoming the industry standard, like, we're talking about a time when JPEG is not the industry standard, right? Like, again, keep that in mind for these papers that we're reading. For image compression technology, there is ongoing research in alternative methods. Currently, there are at least 2 exciting new developments: wavelet-based methods and fractal image compression. This article is intended to provide the reader with an overview and a resource of the research on the latter. We attempt to put the work into historical perspective and to provide the most comprehensive and up-to-date list of references in the field, a truly considerable number as shown in the following table. Right, so it looks like there are 34 papers that were published just in 1994 alone. That this paper being one of them, apparently. So yeah, that's pretty good, right? That's from 1987 to 1994. What is that? That's about 100, maybe over 100 publications, which again says a lot about the field. The organization of this article is as follows. In the next section, we present a brief mathematical overview of fractal image compression. The third section provides an overview of the major advances in the research of fractal image compression, starting from the visionary conception of Barnsley in 1987 and the groundbreaking work of Jacquin, again, I can't pronounce the name, in his 1989 PhD thesis. That explains it. It's a PhD thesis. The fourth section contains 2 tables giving a quick survey of the material included in the references. Finally, we conclude with the bibliography, which could be regarded as the main contribution of this article. I don't think I've ever read an article before where they say the bibliography is the main contribution, but I think in general it's something that a lot of people, like, when you're writing papers, you have to know that most times when people are reading your paper, they're not actually reading your paper. They're going to your paper and then they're finding articles to learn more about how you did your thing, right? So, like, if anybody here is writing papers or, like, doing research, just remember the bibliography, in my mind and also in these authors' minds, is actually usually one of the most important parts of your work, you know? Okay, let's just keep going. So since we explained the mathematical fundamentals involved in fractal image compression scheme only at some course level of detail, the reader will profit the most from this paper when already familiar with the basic concepts. If necessary, such knowledge can be attained by reading introductory texts or reviews, such as, for example, these guys in here, one of which I know we have. And I think we've already read this one, maybe? I don't remember. I think we've found this one, but we might not have read it yet. But we'll see. We believe that here we are presenting a fairly full picture of the literature. Of course, in spite of our efforts, some pieces containing relevant work may have skipped our attention and thus may have been unduly and unintentionally ignored here. My word. This is like one of the most, like, somehow passive aggressive, like, intros I've read. Like, it's like, we may have accidentally missed some people, but, like, I don't know, like, I just feel kind of bad about, I don't know. Anyway, okay. The mathematical principle behind fractal image compression. As a model for the space of monochrome images, we choose a space E of bounded continuous functions, f of x onto g, for simplicity of its mathematical description. The set x taken, for example, as a unit square represents the set of spatial coordinates of the image, while the set g taken as the interval 0 to 1 represents the set of intensity values of the image. So x is the unit square represents the set of spatial coordinates of the image, and G is the interval from 0 to 1, representing the set of intensity values of the image. However, for practical applications suitable for computer processing, one can prefer a discrete framework in which a spatially digitized image is modeled as a point of finite dimensional space. Okay, so this is my first question. How do you turn an image into a point of finite dimensional space? Hey Tim, how are you? For those of you guys who might not know, Tim is a really cool indie game developer. I actually just played Accelerate not too long ago. It's a game that Tim just released on Steam. It's EGG Accelerate. It's pretty dang good. Like, I gotta admit, it was quite fun. I didn't get all the way through it. I got through a few levels, but like, super fun. Really difficult though. The idea is that you're in a car and you have like an egg on top of it, and you gotta like balance the egg on top of the car. It's super fun. But yeah, definitely really hard. Like, I was gonna like do a stream where I was like, I play Accelerate, and then every single time I drop an egg, I have to do a push-up. But like, I dropped like 50 eggs in the first like 10 minutes. Well, I don't know if it was that many, but I dropped a lot of them. Enough that it was like, yeah, there's no way I could have done that. Anyway, if you guys are interested in that type of stuff, check out Tim's channel, and also the games that he makes. He's really cool. So thus a discrete gray tone image of size n by m pixels is thought of as a point in R times n by m space. Okay, so this is actually my question. How is that true? How does an n... Oh, okay, I see what they're saying. They're creating an n by m dimensional space. I thought, okay, no, I understand now. I thought they were saying that, like, you know, here we have our 2D image. This is always going to be in R squared, right? That's what I thought. But no. They're saying each individual pixel is a dimension. Which means if you have a 512 by 512 image, that's not a 512 by 512 image according to this representation. That is a 512 times 512 dimensional space you're dealing with, which is an entirely different prospect. But fine, okay, fair enough. I now understand where they're coming from. That's cool. Insane, but cool. Yeah, okay, we'll go with that. I'm just gonna, I already highlighted it. I don't think I need to circle it as well, but maybe I highlight it in a different color so it comes out as purple. So I recognize that this is actually kind of an important point. Yeah, I'll just do that. Perfect. Okay, after a distance d is constructed such that ED is a complete metric space, the fractal or attractor coding of the image f is seen as the optimization problem. I think this is exactly what we need. So find a contractive operator T on ED whose fixed point G is equal to TG is the best possible approximation of F. The contraction mapping principle ensures that a fixed point TG exists. Okay, let me try to let me think about that a bit. This is what I love and hate about research articles. Like, look, I'm gonna be honest. I genuinely love reading research papers. It's something that I know a lot of people probably don't like. In fact, I'm sure a lot of people have clicked off the stream the moment they see research papers. Totally get that. But I love it. I love it so much. It's super fun. It's just one of those things. It's like it's like a puzzle that you're reading and you're trying to understand at the same time. It's just amazing. Okay, so find a contractive operator T. So T is going to be our iterative function system, whose fixed point is G. G is going to be our image. Is going to be equal to T times G. So the idea is we want some sort of iterative function system such that when we input our n by m dimensional space, we get back out the same m by n dimensional space. So we want something that takes the image, reads in the image, and outputs the exact same image. Sounds stupid, but what it does is it allows us to take in an approximation of the image and output a closer approximation to the image, right? This optimization problem will be approached by means of the Collage Theorem. Now, I don't know the Collage Theorem. That's something I need to learn. That's super fun, guys. Like, I'm like actually super stoked about this. I don't think you understand. Like, I have not done research since 2018, and this is the closest I've come to doing research in such a long time, and I'm super stoked for it. So the Collage Theorem. Let T be a contraction on the complete E by ED metric space with a contractivity factor S and the fixed point G. Let F within E. Let F be within E. Then D, which is the distance metric of F and G, must be less than or equal to 1 over 1 over SD, which again is the distance metric of F onto TF. This is important. Let's kind of work through this one step at a time in just a second. I just wish they could try to dumb down the papers. I do not understand the challenge of that. And at some point, you need to expect the user has some skills, but always impossible for me to understand dense stuff. 100%. Like, that's the point of these review articles, right? This is supposed to be a review article, but as they mentioned in the description, or in the intro here, even though it is a review article, really what they're seeing it is as less. They're seeing it as less of a review article and more as a complete set of references up until 1994. And I think that's important, like, just to keep in mind that, you know, this isn't your typical review article. But yeah, usually if people want, I can go into like how you go about reading a new field that you've never read before, because that's something I love to do. But in general, the process goes by: 1, find an article that you're interested in. 2, find a review article that's cited in that article, read that review article. 3, find the keywords, Google those, find those review articles, and after you've read all the review articles, then you can go back to reading the actual paper. And that's generally what you do to get through the mathematical, specifically the dense mathematical papers. The math notation can get dense and annoying, but from my experience, it gets a little easier as you keep trying. I read mechanical engineering papers mostly though, so your mileage may vary. If you do that, please find a way to share that with me personally. If I do what? If I like have a guide to reading papers, back 2 levels of review articles. Yeah, no, I mean, that's the thing, right? Like, so I'm the type of person, like when I was younger, like I might consider making like a YouTube video on how to read a research paper. In fact, maybe people would be interested in that. Maybe I do that this weekend. Like that would be, maybe people would be interested in that. But I don't know, like we'll see. Basically, if I can't solve a problem this week, I'll make a, like, if I'm unable to finish the question, which is, you know, how do I know if I'm attracted to the Sierpinski triangle or not? If I'm unable to solve that question by this weekend, I'm actually going to take a step back and we'll make a video on how to read a research paper. I love this, to be honest. Never thought that watching someone read papers on stream would be fun. I'm happy you enjoy it. Sometimes you could just run into a topic you're completely unprepared for, though. Let me tell you a story, my dear friends. So, when I was younger, I don't know why I'm so excited about this. When I was younger, I used to carry around 2 books, and you guys are gonna laugh at this because you're gonna hate me and because of this. But one of them was an interlinear Bible, and I'm sure I can find this. And you guys are gonna, I know some of you guys are gonna be pissed off, but let me show you this book. This was the largest textbook I had ever received, and it was just the Bible in 3 different languages. I loved this thing. I loved this thing to death. I would read it in and out. I loved studying this thing. Not necessarily, I was, I guess, a religious nerd at the time. Like I read way too much of the Bible, but there was something about like just studying things in a way that no one else had studied I quite liked. But the other book I carried around was a book that was equally as big, called Niedermeyer's Electroencephalography. Niedermeyer's EEG will probably bring it up. Too many E's. That was not it. I'm looking for the exact book that I had. Here it was. It was about twice the size of the Bible, and my backpack always had both these books. The thing I loved about this book is that I was always completely and totally out of my depth. I never understood anything in this book. But what I loved about it was that every once in a while, as I was reading, I would try to pick apart what was happening in the book. And they would say something. They would say something along the lines of, this thing is a new area of research that people are currently looking at. And I was like, man, that is the most motivating sentence I've ever heard in my life. Just people saying this thing has not been figured out before, from someone who like just loves just like the idea that you could discover something that no one's ever discovered before just by reading a book. It was just amazing, you know? And that to me was like, that was the moment that I was like, man, I really want to do research for the rest of my life. I don't know if I necessarily thought it was research at the time, but the concept of just doing things that no one's done before, that was the moment. I was like, this is what I want to do. And I don't know, ever since, I've just loved reading research papers. And so basically, I guess it's not so much of a story, but from that, I kind of crafted the ability, from those 2 books, I've crafted the ability to like learn basically from any perspective, from the perspective of like old historical literature to like new literature that's kind of on the cusp of human knowledge. Like this ability to go back and forth is incredibly important. And I feel like I have a unique perspective on it that a lot of people don't have. What do we have here? I'm trying to read graphical coding things like this or vehicle dynamics physics papers like this. And I do sometimes get through it, but it takes a load of effort. Right. I mean, that's the thing. I love doing it so much that like, it's not even like, for me, it's like, this is amazing. Like any day I would take a dense research paper Like just a 3-page research paper. It's going to take you 30 to 40 minutes to go through, but I would go through that any day when compared to like a 30-minute YouTube video. I love reading the papers. I don't know why. I'm actually working on a spatial kinematic dynamic solver as an extension of Eigen library. Oh, cool. Yeah, I've used Eigen before. I can confidently say it would probably be quite hard if you had no background. No doubt. Like, no doubt this stuff is hard. Chester Wheeler, I'm building a physics engine myself for a racing simulator. It's a challenge and I'll push through it. I mean, honestly, Tim, I'm sure it's going to turn out well. I'd like to do that for something in green engineering, all in C++, very inspiring. Here's a book on spatial dynamics that might help you. No, this is great. I mean, links are allowed in the chat just for this reason. I'm happy that you guys are chatting. Anyway, I'm so sorry. I kind of went on a tangent there. The point was like, I don't know, there's just something about like, there's something about reading research papers, you know it's messy, you know it's dirty, but like at the same time, you know that like at the time that you're reading this research paper, that thing that you're reading, by the very fact that it was published, you know, in a reputable journal, means that was at some point in time the boundary of human knowledge in that field, and that in and of itself is incredibly exciting. And anyone who says otherwise, like, I don't understand their logic. Like, you're okay with like watching someone do a world record of the number of hot dogs they can fit into their mouth, but when you see something about fractal image compression, you're like, all of a sudden that's boring? Give me a break. Like, it's totally awesome. Like, I don't know. It's just one of those things, you know. Anyway, let's go through this one more time, and we're gonna try to piece apart this this particular equation here. I say that all, and then I do what might be kind of boring to some people, where I just go through an equation in a math paper. But hey, you know, like, I think it's cool. So just don't judge me. I already have so much judgment, I'm sure. No, I wanna do a blue S. That's what I want to do. Ah, come on. Perfect. 1 second. I'm almost there. All right, now we can read now we can read the equation. Why did that do that? 1 second. I have to do that again. Sorry, look. Don't judge me. I know you guys do the same thing. You know, if you see like, yeah, you're gonna color that in. Like, I know you do that. What do we have here? I'll take a peek next time we get there. I think boring is in this case. I don't want to think about it that hard. That's probably fair, right? Like, I don't know, it's up to you guys. For me, I find this stuff like absolutely fascinating. I genuinely love it. Okay, so what are we reading here? I completely forgot what we were doing, so let's go back to it. So if d of f of g is less than 1 over 1 over s, 1 over 1 minus s. So s here is your contractivity factor. That's how much you're smushing every time you do an affine transform, right? So I have a video on affine transforms, but essentially, like, you know, a contractive mapping is something that takes a square and transforms it into something that's smaller than that square. You know, it could, or the same size, right? So what we're saying is, if your contractivity factor is 1, or less than 1, then what you want to make sure is that 1 over 1 minus s, and again, s can only be up to 1. So that means that you're going to be multiplying this by a factor. So if you're contracting a lot, then what this ends up doing is, actually, I don't know if the contractivity factor goes up or down. It could be as you're contracting, it grows bigger. Like your contractivity factor of 2 might mean it's half the size. I'm not sure exactly. That's something that we have to figure out. So how does the contractivity, does S go up or down as you get smaller? That's my question. S big or S small as you go, as your size drops? That's the question. I don't know. I really don't know the answer to that. We'll try to figure it out. You've got a problem if it's 1? Oh, you definitely have a problem if it's 1, right? So like, we'll see. So d then is the distance, I believe. We just said it was a distance. Yeah, d is a distance, d here. Is constructed such that e of d, 1 second, let's go back to the highlighting here. And I'm going to make it so it highlights in blue, or pink again. D is a constructed such that whatever. So D is your distance. So this is the distance from F of G is the same as F to T of F, where T of F should be equal to G. Yeah, perfect. So all we're saying is that there's some contractivity here, but you have to make sure that the distance of F, which is a single point in your metric space, should be just as far away from G, which is your final image, as it is from T times F, where t is going to be your function system, and f is going to be your endpoint point. So again, up here we said g is equal to tg. Let me change over here. G is equal to tg. So t again is your set of functions. So this is basically saying that g is going to be equal to t times g. So in the same way, f should be equal to t times f. So f and g, the distance between these two should be about the same as the distance between these two. Now again, this guy, the question is, what does the contractivity mean? And that is a good question. Also, I'm now realizing that maybe like a sharp blue on a pink highlight might not be the best way to do this because my eyes are kind of bugging out. But yeah, that's okay. Sorry, I meant that people say that reading paper is boring actually probably mean that they don't want to focus thinking about it that hard. Not that you're reading this paper is boring. No, actually, I totally understand if you say reading this paper is boring. Like, I get you. I 100% understand. I actually find it way more enjoyable to just like, I said something one time in the middle of my PhD that I still stand by to this day. And it was that there is nothing in my mind that is more enjoyable than sitting down with a cup of hot cocoa and just reading a paper. Like, that's it. That to me is like, if I could just do that for the rest of my life, I would do that for the rest of my life. I genuinely love it. And I know other people don't think the same thing, but like, again, like just the very fact that every single research paper is like the boundary of human knowledge at that time is just, it's such an incredible like concept, that I don't know, like I just, like all these people like watching videos on the Magnus effect or whatever, like the longest football shot over, you know, a chicken alley or something, whatever the next world record is that they're looking at. I don't know. Like, I just feel like they don't understand that paper, a single academic paper, is a world record. I don't know. I think it's cool. I love it so much. You know, maybe next year I'll think differently, but I'm just so happy to be able to read the academic literature again and just like actually reason about it, which I wasn't able to do for the end of my PhD, and I wasn't able to do at the end of during the postdoc either. This is the first time in a very long time that I've been able to do it. I feel that passion from your enthusiasm. It fuels me to enjoy it more, and honestly, I do enjoy reading something hard and dense when I get the aha moments, right? And that's exactly why I think like content creators like 3 Blue 1 Brown, for example, are phenomenal, right? Because they give people that aha moment, like, in a way that's way more accessible, you know? I find that I enjoy reading them. I hate trying to write reviews. Okay, reviews are another like thing entirely, but that's, to me, the problem with reviews has to do with the problem of academic writing to begin with. Like the fact that, to do with the fact that, sorry, like, you know, reviews are like unpaid labor that you have to do to get, it's just a whole thing. I ran the numbers. S is 0 if it compresses everything to a single point. Okay, so S does go... Okay, if S is 0 when we compress to a single point, then this doesn't work if there is no contraction. So there must be a little bit of contraction. Yeah, there must be some amount of contraction, which makes sense because if we have, let's say, a square, right? And it's contracted onto this diamond, right? And we have a single point F here, right? What we're saying is that the distance from this to the square, and then the same point here, should be from that to the diamond here. We're saying that because the diamond has been made smaller, we're going to have to increase 1 over 1 minus S. We're going to have to increase it a little bit to make up for the fact that it is smaller. So we have to like basically take into account the contraction, I think. So if S gets smaller as you contract down, then that basically means that this value here, doesn't it also get smaller as you contract down? Because if you go S is equal to 1, right, then this is going to be infinity. If S is equal to 0.995, then this is going to be equal to basically very close to infinity, right? So how does that make sense? Because if this is like super close to infinity, I'm gonna put a pin in that, and we're gonna come back to that later, because I'm not happy with that logic yet. I'm sure it's right. I just need to think about it a bit. But that's okay. We have a lot more to go through. Simple example, t of x is equal to s times x. G is equal to 0. T of x, x is some point, is going to be equal to s times x, where s is a contraction, times x. So if x is equal to 5, then s times x is going to be equal to some contraction times 5. And g, what is g equal to? G is the fixed point 0. Okay, so you're saying we have g is equal to 0, and then we have, here's your number line, and then we have some x. X doesn't matter, but we'll just say, for the record, give it a value of 5. And then we say t is a contraction mapping, which is going to be s onto x. And so, yeah, it must go smaller. Yeah, you're right. Okay. Again, we're going to come back to it, but I think you're right. I just need to think more about this equation here, a little bit more. So, thus, by minimizing the distance between f and t of s, the collage of the image, we hope to minimize the distance between the fixed point g and the given image f. Okay, I think that's fine. I was getting f and g mixed up, so g is the point and f is the image, but I think that's okay. The image times t and the image is fine, so I think that's okay. Of course, if the value of s is close to 1, nothing ensures that this method provides a good approximation. Yet, this was the original idea of Barnsley, and most of the fractal-based algorithms rely on the same approach. The fractal compression scheme can be viewed as 2 consecutive steps. Okay, that's fine. I agree with that. Okay, it consists of the construction of the operator t. So the encoding process, see figure 1, which should be down here. It consists of the construction of the operator t, which will be defined by a set. Okay, the set R of R, okay, called ranges, form a partitioning of X. The set D of R, called domains, so ranges and domains, perfect, are also a subset of X, but may overlap. For each R, so for each range a domain R exists, which is a bijection, U of R of D onto R, and a contraction V of R on G equals G, are chosen such that the distance is as small as possible. So D is a domain onto a range, and then V is from G into G, and G is going to be what? What is G in this case? G is... What is G? I should know that. Why can't I find G? Okay, that's okay. This map adjusts the intensity values. That's okay. F of x equals big G. Oh, it must be the set. It must be the set of all points in space. That's totally fine. Kyle Wiggs, thank you so much for following. Really appreciate it. Hey, Raid, how are you? I hope you're having a great day. Okay. Did you have a different name before? Or was it always Raid Lancia? Because I feel like I don't recognize the name, but I do recognize people that would say, hey, my man's back. So... G is a set of group elements. I think that might be it. So G might be the set of all little g. Let me write that down somewhere. G is going to be the set. How do I notate that? I'm just going to say within big G, which isn't right. It should be like little g. A big G is like same name. Oh, fair enough then. How are you doing, man? I hope you're having a great day. Okay. Chosen such distance. Okay, so we're looking for something that is chosen such that the distance d is as small as possible. This is simply realizing the condition that f is equal to t of f locally. And again, I do think we need to highlight that locally here. By exploiting the redundancy contained in the image, since we seek for each part of the image corresponding to a range similar a similar part corresponding to a domain, right? Finally, the operator t is given by t of f is equal to the sum of all tk of f, and little t of x is equal to the sum of, is that lrk? X. So this is where I'm lost on this one, but saying that big T of f is equal to the sum of all of the t of f's put together is basically saying that we've taken the image, we've parsed it up into a bunch of smaller domains, and basically done a transform in each of those smaller domains. That's fine. This guy is a little bit confusing to me, so I figure we look into that. G is taken on the interval 0 to 1 is in parity. Oh, you're right. It literally said that. Yeah, it literally says right here. I'm just stupid. That's it. I just got so into chatting and talking about how I love research, and then I just didn't even read the article appropriately. And they don't even really describe what this is saying. So, L of RK here, and then U, -1. And then little t. So, I'm not seeing where these are defined, but let me see if we can figure out in figure 1. So elements of the fractal code. Left is the partitioning of the image region, a square into ranges. Yep, that's fine. That's what we expected. Center is some of the corresponding domains. Okay, so I don't exactly know how R1 over here is related to D1 and R2 is related to D2. Maybe they don't have to be specifically related. But here we do see that RK is moving into DK. So that's a question that I have. Center some corresponding, right? The affine transformation VK for the kth domain pair, domain range pair. For each domain range pair, DK, RK, there is an invertible geometric transformation, U of K is DK onto RK. The function F evaluates image intensities for a point of X within RK. We compute its pre-image UK. That's what I needed. UK is a pre-image minus L in the corresponding domain D. Look up the image intensity F here. There we go. And finally apply the affine transformation VK. Obtaining T of F is equal to this guy. Okay, no, that makes a bit of sense. 1 is the characteristic function of RK. Okay, need a bit of explanation for what a characteristic function is. I'm so sorry. I know I shouldn't, but I'm dumb. Just, could you give me that? Okay, decoding process. See figure 2. The decoding process consists of computation of the fixed point. This is accomplished by iterating the operator t upon any initial image f0. Since the contraction operator t is contractive, the contraction mapping principle ensures that the convergence of the sequence t of f to the fixed point. Okay, I'm a bit confused by the image here. Let's try to parse this and figure out what they're trying to say. And let me get some water here. I have 110 push-ups to do. I just remembered that. I don't think I have the push-ups displaying on screen. It's a function that is 1 on RK and 0 otherwise. Right. Okay, thank you. That's what I needed. Okay. Wait, why is it not showing? 1 second. Let me go back over here. I should be on... Oh, because I pressed the wrong button. That's why. The workout wasn't showing. I just wanted to put it back up there. Okay. Encoding and decoding for a one-dimensional example. Let f of 0, 1 onto 0, 1 denote the image to be encoded on the left. Okay. We choose the same domain 1/2 over L for all ranges shown on the left. Note that the graph of f in R1 as well as R3 is just a scaled down copy of the graph in the domain. In R2, we can reproduce f by a vertical flip of the same copy. In R4, we use the copy with an additional offset of 1/2. The code thus employs the geometric transformations. I'm being lost a bit in the affine transformations here. When reconstructing the original from the code, we may start with an arbitrary image g and repeatedly apply the image operator t. The first two iterations t of g and t squared of g are shown for the choice of g of x equals x. This setup is called the local iteration function or a partition iteration function system. So I'm just going to come out and say it, that if this image over here is supposed to be reconstructed, if this image over here is supposed to be reconstructed form of this image over here, I think, unless I'm dumb, they did a bad job, right? Because this guy kind of, you can clearly tell where this line goes, but this one does like this whole thing. You know what I'm saying? Like it's kind of there, but like I wouldn't go about, you know, bragging to my friends that I just reconstructed an image from this guy. Now, a lot of the rest of this paper is about the history of fractal compression. And what I'm actually interested in doing is taking this review and looking at forward citations from this review to see kind of where people have taken it, and to see what came after this before going back into the history, right? If I was reading this alone, I would definitely read through the history here. Like, I'm fascinated myself, but like, I feel like, you know, I'm on stream. Let's go ahead and do file, save, and let's take a look at the forward citations here. So we're going to do saha.zop. Perfect. And we'll have that saved for the next time we look at it. Okay, so the next thing I want to do is look at the forward citations for a paper that I just forgot the name to. Review of the fractal image compression literature. All right, let's go to Google Scholar. Scholar review of the fractal image compression literature. Perfect. Cited by 79. Let's see, what is the latest citations? It says 2021. It's actually got 3 citations this year, which is pretty good. Comprehensive analysis of the image encryption and compression techniques with the assessment of performance evaluation metrics, a novel secure communication scheme based on chaotic modulation, recursive encryption, and chaotic masking. What does that mean? All right, let's do since 2020. What I'm looking for to see, so these are the same papers since 2020, 2017. It looks like there wasn't much actually published. Yeah, in fact, this is about what I expected. So in the past 5 years, there hasn't been 4 years, to be fair. There hasn't actually been too much being done here. Survey on data compression techniques from the perspective of data quality, color coding schemes, and data type and applications. I feel like we should read that one. Representing fractals by super oscillators. Oh, come on. We have to peek into that one, guys. Come on. Don't leave. I have to at least look at that one. Article PDF. Sure. It's Journal of Physics A, Mathematical and Theoretical. Representing fractals by super oscillators. I'm just taking a look at the images here. So this is one of those papers that, if you were to read it, I can guarantee you would take like an hour. Like, you know it's going to take a while when it's like 3 pages with a bunch of like these types of diagrams. Is it worth reading? Probably not right now. We can probably just skip it for now. Okay. But what this is telling me, which is nice, is that what it's telling me, which is really nice, is that it doesn't seem like the field has advanced like significantly far past this review, which is what I was hoping for. Because if it hasn't evolved significantly far past this review, then that means that potentially what we're reading in the review is fairly accurate, right? What I'm afraid of is the review was written in 1994. That's almost 20 years ago now. Like, it's 18 years ago. To have a field of computation stay stagnant for 18 years in the current landscape of computer science research is highly unlikely. So this is where, in some sense, I feel like we've hit a gold mine, in a way, because it's like, hey, this is something that was once really interesting. Now no one's looking at. Why aren't people looking at it anymore? That's the question. And probably because they found that wavelet, image compression was just better. Because if you look at the images that we were just looking at, in a sense, it is kind of wavelet-esque, and the way that they're splitting the domain into a bunch of subdomains and everything. So let's open this up again in .zop, and let's just see what the other like papers were saying around this time. And I think that's probably it's probably a good place to go. I love and hate that I'm just reading this on stream, though. Like, I feel like I should be reading it on my own. Okay. So fractal image compression is based on the concepts and mathematical results of the iterative function systems. The roots of this theory are at least 10 to 20 years old. See the work of Williams and Hutchinson. Then in the mid-1980s, iterative function systems became very popular. What about compression using quad trees? I guess it might be related. There definitely are like related ways to do compression via like quad and oct trees. In fact, I think that's what JPEG does, doesn't it? Oct tree. Because I think it creates an RGB color space, I think, and then it compresses along I think it does some form of color quantization for that. Let me just see what we have here. In 3D computer graphics. I want to say this is what they use for JPEG. Maybe not. Maybe if I scroll down, it will say. binary, linear octree, voxel, quad tree, JPEG, image compression, octree. Let's see what we got. Octree-based point cloud compression, compress images online. Let's get back over here. G. Octree approximation to compression methods. Oct squeeze. Let's do quad tree instead. Because maybe you're right. Maybe they do use quad tree. I would just find it surprising to use a quad tree when, you know, you have an RGB or HSV color space, which is inherently 3D. Quad tree. Quad trees for image compression. Let's go. Okay. I was wrong. You were right. Look at that guy. What I'm assuming they do is they use a quad tree on top of an oct tree. Again, like, there's more information on using quad trees than there are for using oct trees, but they definitely do some form of color quantization, right? Like, I think. Oh, maybe not. No, it looks like each of these squares still has, or each of these quadrants still has a gradient along it, which is surprising to me. Yeah, that is actually kind of surprising to me. So my next set has 110 push-ups. I'm not going to be able to do 110 push-ups. I don't know how. Swoleos thought I could do 110 push-ups. I'm gonna do as many as I feel comfortable with, and that's what we're gonna do for the next set. JPEG is a 64 dimensional vector algebra with some rounding. Fair enough. I think this gradient is an optical illusion. Maybe it is. Maybe. I don't think it is. I mean, if you look here on the graphics interchange format file, I mean, it's not just an optical illusion. It's clearly there. Oh, but maybe, okay, what could be happening? Let's take a look at this again. What could be happening is, okay, each of these quadrants, okay, I see what's happening. I understand now. Okay, so each of these quadrants has a coarse resolution associated with it, right? So as you go further and further in, what ends up happening is each quadrant is more and more defined. So this square over here is getting more and more defined, which is creating a gradient, because it's just getting more defined as you go further in, right? Like, as you have more quadrants associated with it. It's just that this particular square is defined against the square right next to it, and so it looks like it should just be one big square, but I think it's actually a bunch of smaller squares put together. Or just maybe not as many squares as the guy right next to it. So what I'm trying to say is that, yeah, if you look at these squares in here, I think these don't have gradients associated with it. But I think these guys do have gradients associated with them. Thanks for decreasing the set difficulty. I was actually just going to do that on my own. I was going to use my own channel points, which is kind of cheap. But how many push-ups did that decrease by? That's fine as well. Oh, Chester, my friend, what are you doing? Anyway, what do we have now? We have, okay, how many was that? That's a decrease by 2? Decrease, so we should be on difficulty 2, which is about as low as we can go. How many push-ups is that? That's still 50 push-ups, which is doable. Let's do 56 push-ups. That's what we're calling it. Perfect. 56 push-ups. Let's go. We're going to go ahead and do the exercise at the top of the hour. We're going to get back to reading the rest of this paper. And I think maybe that's what we'll do today. We'll get through the literature, just kind of try to figure it all out. I know, like, I don't have a really, like, good way for people to spend channel points right now. So we're going to get through the literature. For those of you guys who are new, you haven't been here before, we basically take a 5-minute, we can decrease it one more time if you really want. Decrease to 1 is as low as we can go. So quadtree leaf usually only contains a flat color. It might be interesting to use a hybrid there. Raster graphics at each quadtree leaf. Definitely. However, I don't know if talking about... yeah, okay. So here's what we're going to do. We are going to continue. I think going through this paper, just kind of figuring out... Okay, we'll talk about what we want to do with this after that. But what I'm going to do is we're going to do 38 push-ups. Which is somehow the lowest difficulty we can go. We might be able to go a bit lower, but 38 push-ups is apparently as low as Swoleos will let us go, which is insanely high compared to what it should be. But for those of you guys who are joining from home, you haven't been here before, what we do is we do a 5-minute exercise at the top of every hour, followed by 55 minutes of a project. What this allows us to do is really just hone in to focus ourselves during the 55 minutes, because we've given ourselves a 5-minute break and some sort of exercise just to get the blood flowing. So we're going to go ahead and do that. Thank you, None More Grim, for following. So for those of you guys who are here specifically for the fractal compression, don't worry, we're going to get back to it in 5 minutes. For those of you who might just want a quick 5-minute break, go ahead and take that now. Otherwise, just going to move on to the 38 push-ups that we have left to do, and then we'll hop right back onto the fractal compression discussion, which I think we've actually made some good progress here. I'm pretty happy with it. But there's a lot left to do. So I'm going to be right back, guys. Going to change the microphone position and switch the music, and then do the 38 push-ups and go from there. Okay, so for those of you guys who might be joining at home, you guys don't have to do 38 push-ups. You don't have to do a single push-up if you don't want to. The point is just to get up and just get the blood flowing, however you want to do that. I'm going to be doing 38 push-ups, which is still a lot. I'm going to change tool layouts right now to make it so next time we get push-ups, it actually cycles through slightly fewer push-ups. But yeah, 38 of them, so I'm going to do 2 sets of 19. That's what we'll do. Again, if you want to do it at home, I don't recommend doing 38 of them. Do however many you feel comfortable with, whether that's 1, 5, 10, 15, 89, whatever you feel comfortable with. And yeah, go ahead and do that. And again, we'll get back to fractal compression in like 5 minutes or so. All right, 2 sets of 19. Oh, okay, let's go. Okay, let me move up a little bit because I'm gonna hit the microphone if I do it here. All right, 3, 2, 1, and go. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. One more set. What do we have over here? I don't see anything in chat. So again, we're gonna do one more set of 19, give myself just a few seconds of rest before moving on to the next exercise. Again, if you're doing it at home, just do it at your own pace. The point isn't to make yourself super sweaty in the middle of programming. The point is to just kind of get the blood flowing, and really just focus on something else for about 5 minutes before getting back to the work that you do every hour. So, whew, took a lot more energy than I thought, though. Okay, another 19. Okay, and 3, 2, 1, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 12, 13, my counting's awful, 14, 15, 16, 17, 18, and 19. Alright, that was 2 sets of 19. Gosh, push-ups, I hate push-ups so much. Why do I do 1 push-up per hour? Why not any other exercise? Anyway, that's it for now. Back to fractal compression. Okay, I've got to do 2 things before moving on to fractal compression. The first of which is modify swell layout so it doesn't output as many push-ups. And the other thing is change the music. Music first, while I'm still breathing incredibly heavily from doing essentially 40 push-ups. And now for the swell layout fix. So in here we're just going to go VI, exercises, and then arms. Okay, what are we doing for... Push-ups goes up to 200 push-ups? I'm just gonna drop that down to be 100 push-ups. And that seems reasonable to me. Also, 100 pull-ups. No way, dog. There's no way anyone's gonna do 100 pull-ups. You kidding me? In the case that we accidentally get pull-ups, I don't want to do 100 of them. I think what I initially had it set as, by the way, Manda XZ, thank you so much for following. I originally had it set so that, like, my idea was that a 10 difficulty would be like Olympic level athlete. But now I think maybe 10 difficulty should be as much as I'm comfortable in doing on stream. So I think I might change the difficulty of a lot of these in the near future. Okay, so let's get some water. And I think what we're going to do is just kind of... Here's a question I want you guys to answer. Should we read through this overview of fractal image compression research? Or do you think maybe we should try to find another paper that's not from 1994, that might be a bit more recent, that does the same thing? Also, I'm going to cycle the next set. Bicycle crunches. Yeah, 165 bicycle crunches. That sounds fun. I'm actually looking forward to that one. So what do you guys reckon? Should we do... I'm going to try to find a newer paper. I did just look in Google Scholar, but I'm going to look again. And we're going to do custom range, and it's going to be anything from 1995. 1995. This one doesn't have too many more pages. It literally just has the overview. So it's just the next few pages are just text. There's no images associated with them. So it's kind of long. Yeah, we could. The problem is, like, skimming things on stream is really difficult because as you start skimming through things, like, it just becomes completely unfollowable. But maybe we can look at this, right? So they've got basic iterative function systems. And then down here they have local iterative function systems. So to provide a rapid overview of the papers contained in the bibliography, we propose two tables. The first is devoted to works using the basic iterative function system method. The second table deals with papers that consider local iterative function systems. The bullet symbol indicates the topic that was stressed in the paper. So essentially what they're saying is, what is FL? Is this genetic algorithms? What is SA? What's riffs? Oh no. I can't read it because I decided to skim the paper. Okay, first I'm going to look at Google Scholar, and we're going to see what Google Scholar outputs. So we're going to search from 1995 and just see... In fact, you know what? Screw it. Let's just go back a few times. It said, then you're right, it did, didn't it? I was just dumb. It definitely did. It says right here, I'm just stupid. Oh my gosh. Let me just erase all this and just make sure no one clips that part of my Twitch stream, because oh, that's pretty dumb. So obviously 1D, 2D, 3D, P is partitioning of the image, DEC is decoding, FBB is fixed basis blocks, encoding, MM is moment method, FI is fractal interpolation, GA is genetic algorithms. That's what I want, actually. So actually, we might want to look into these papers because we were eventually going to be using genetic algorithms with Fractal Flame. SA is simulated annealing, and RIFS is recurrent iterative function systems. Down here we have local iterative function systems. Do any of these guys use? No, none of them use. None of them use genetic algorithms down here. Or papers that cite those papers. Right. That's kind of what I'm looking for right now. The forward citations from this paper. And I'm just going to look at all the citations and see what looks right, you know? But again, just for the record, everyone, I have been streaming for about 2 hours. So I think at the end of this hour, we're probably going to call it. Just because I do have to, be out by 6. I think what I'm going to end up doing is just reading a lot of these papers on my own, which again, I'm super excited to do. I'm so excited, guys. Like, I can't explain how excited I am. Okay, so I do have a question here as to why we have decoding down here, but encoding here. Why are there so many more papers that do encoding than decoding, right? Like, you would kind of, or rather, I guess that's not my question. I think that makes sense. But my question is, why is encoding after decoding? I would have naively thought that the decoding papers would come after the encoding papers. So this one only does decoding in 94. Encoding, and I think that is kind of what it is. So if you look at this paper from 94, it does decoding. If you look at this paper from 94, it also does decoding. This one does 93 decoding. But if you look at the encoding papers, well, I think, again, this paper was published in 1994. So I think decoding was slightly harder than encoding, I think. At the research delaying team, what methods are you looking at? We are currently looking at fractal compression methods. There's a review of fractal image compression literature. And again, the reason we're looking for this is it is very related to what we want to do for the end of the project, which is turn any image into a set of fractals. That's literally what fractal image compression does. But the other reason we want to do this is, again, we're trying to find kind of a distance metric from any point in space to its attractor, right? Which is almost literally what this distance metric is. Like that, this is actually what we're looking for. The question is, how do we do that more generally? Man, that was not what I expected to happen. But yeah, this distance metric in here is what we're looking for. They don't really go into detail about how it's calculated, but I think a lot of these papers will, which I think is really good. So essentially, as long as we can find a methods paper for any of the fractal image compressions, literature, I'm almost positive we can find what we're looking for. So this is really good. Like, we've made some good progress today, you know? Okay. So I'm going to just kind of go back a few slides here until we go here, review fractal, and this is cited by 79 people. Oh, was I already just looking at, okay. Yeah, this is fine. Should we search within citing articles as well? Fractal image compression based on Delaunay triangulation and vector quantization. Do we want to go into Delaunay anything? I feel like I don't want to go into Delaunay anything. Anytime I think about Delaunay, I get confused. Accelerating fractal image compression by multidimensional nearest neighbor search. This must be to find the distance metric earlier. Like that must be what that is, right? Let's look at it. Let's see what it is. Fractal image compression. The encoding step is computationally expensive. A large number of sequential searches through the list of domains portions of the image are carried out while trying to find a best match for another image portion. So this is obviously on the encoding step, but our question was about the distance metric, and the distance metric is on the decoding step, isn't it? Or am I dumb? I think it's on the decoding step. So I think this might be about something different, but let's see what we have here. This result, our theory developed here, shows that this basic procedure of fractal image compression is equivalent to multidimensional nearest neighbor search. This result is useful for accelerating the encoding procedure in fractal image compression. The traditional sequential search takes linear time, whereas the nearest neighbor search can be organized to require only logarithmic time. They were using... No way. They were using linear time searches for nearest neighbor. Yeah, okay, fair enough. Right, no, this is perfect. To take a logarithmic time, this might be what we're looking for. Because if you guys remember from maybe an hour ago, this question of how do we tell how far away we are from the Sierpinski triangle really only works assuming that the Sierpinski triangle is a series of lines. If it's a series of points, then the nearest neighbor search would be the naive way to do it. But using a multidimensional nearest neighbor search, kicking it down to logarithmic time, that makes sense. Like, this is almost exactly what we need. The fast search has been integrated into an existing state-of-the-art classification method, thereby accelerating the searches carried out in the individual domain classes. In this case, we record acceleration factors from 1.3 up to 11.5, depending on image and domain pool size, with negligible minor degradation in both image quality and compression ratio. Yeah, I'm gonna move this into the Flamify directory as one of the ones that I want to read. So let's go ahead and move downloads. I think it was 00 something 5. Here. Okay, that's definitely one that I want to read. Just because I think it's almost exactly what we're looking for. Fractal image compression, an introductory overview, but this is a book. okay. If you're giving me a PostScript book. Oh no. It wants to open it in GIMP. I'm fairly certain we can't open this up in GIMP. Wait, oh no. I lost it. What is this going to be? This is going to be, convert to PDF? Yeah, I'm sure. How do you do PostScript to PDF? Let me go over here, CD downloads, ls here, ocular, let's just do ls_.ps. We only have one, so let's do ocular Ralph. There we go. It worked. We opened it up PostScript. Okay, great. How many pages is this? It might be just a chapter of a book. Fractal image compression and introductory overview. This looks way nicer than whatever we were just reading. Oh, never mind. It's getting a bit, it's a bit mathy. Visual shape codebook. But, you know, it's using words that I know. Codebook. I know that word. Yeah, this looks like one that, ooh, now that's a nice image. Figure 8, result of 2 encoding using quad-tree partitioning. Who said quad-tree? CMDLP. There you go. Apparently, this is like effectively used here as well. How about we? This is a long guy though. It's 64 pages long. I feel like we might already have it, but let's go ahead and move it over. Just so we have it. Move, downloads, and then RAOUF. Perfect. Okay. Let's just keep looking to see if we find anything interesting here. Did I close the? Yeah, I might have closed the tab. I got it back. Fractal image compression and introductory overview. Oh, we just looked at that one. Nearest neighbor search. Again, that looks like how is this guy after this guy? I don't. Via nearest neighbor search, 25 pages. Surely this is just another. Yeah, like I'm fairly certain I know what this is going to talk about. We'll skip that one for now. Okay, what else do we have here? Iterative function system, fractal interpolation for 2D and 3D visualization. Is it the same author? Oh, you're right. Yeah, this might be their thesis, and that might be a paper related to their thesis. That might be how it is. Fractal image compression and recurrent iterative function systems. That is from. Let's see if we can get something new from at least 2010. Sort by date. Abstracts everything. Let's do custom range, and we're gonna do something from 2010. See if there's anything new in the field from 2010. 92 days ago. Wait, was there? No, there was some stuff from 2021, which was surprising. But then if you look at it, there's something from 2020, 2021, and then like 2017. So there was nothing from 2018 or 2019. Survey on image compression algorithms for visual sensor networks, representing fractals by super oscillator. Yeah, we saw that one before. Fractal-based image encoding and compression techniques. It doesn't look like it's from a reputable source. A review on fractal image compression from 2014. That one looks relevant and useful. Review on fractal image compression. Actually, maybe this is what we want. Yeah, I'm happy with that one. Okay, let's grab this one as well. I'm going to be searching through these on my own. Apparently, fractal image compression was like super useful for fingerprint scanning, and that was what it was like particularly known for doing. Which is, I don't understand how. I don't understand how. Like. I feel like I'm so stupid, and I don't even know what question to ask related to it, you know? Oh, but this is interesting. Advantage of fractal compression. Resolution and device independent. Decompression is 6 times faster than JPEG. Really? Superior for high compression ratios. Really? Okay, interesting. Compression ratios can be improved by taking more time during compression without any increase in decompression time or increase in image quality. Disadvantages. Compression time takes 12 times longer than JPEG. Okay. An unproven technology, it's expensive for small users. Fair enough. So if we cut down compression time, hey, that's what we need to do. Just work on compression time. That's our field of research. JPEG is good where low compression ratio is required. Basically an industry standard. It is free. Disadvantage of JPEG. JPEG cannot work on binary images, cannot work well on images which are non-realistic. And quality of images degrades seriously with high compression ratios. Apparently removing image result gives a result on fractal compression in soil. Oh, what? Fractal techniques can also be useful for sound and motion videos. There's a fractal compression version of MPEG, which can be used to compress real-time videos. I want to read it. I want to see what it does. So a review on fractal image compression will also come over here to this guy. So move downloads, a review on fractal image compression, bring it over here. Also, guys, like, I know, I'm sorry, I'm like geeking out this entire stream. I realize that. Like, I don't think you guys realize, I've mentioned this before, but how much I just genuinely love reading research papers. Like, I usually, like, avoid it from stream, because every time I do it on stream, people say I sound, like, really manic, because I just get really excited. But, like, there's just something about it that I just enjoy. Like, I love just this, you know, being slightly over your head, but not over your head enough that you know you can't figure it out, you know? Like, it's something you can't get, I can't get from any other experience, you know? Like, how like, you know, you don't want to play a game that's too easy, right? You want to play a game that is sufficiently challenging enough that, like, you know, like, you learn something as you're playing, right? What about integral images? Using them speeds up various calculations on images. What are integral images, actually? Could you link me something that I can look into? Okay. So let's remove that, and let's see. A review on fractal image compression. Let us see if there's anything from 2017 and onward. Perfect. Classification and data compression. Image denoising, wavelet variants for 2D analysis. Okay, so let's go back to what we were looking at before. Which one did we look at? Review, this one. This one's cited by 3 people. Research on new algorithm for accelerated Okay, I'll take it. Research of a new algorithm for acceleration of fractal image compression. This seems like what I want. PDF? Ooh, it gives me a PDF and everything. All right, let's see what we got. Research of new algorithm for acceleration of fractal image compression. Yeah, okay. This is exactly what I want. Yeah, perfect. I mean, look, it's this looks like a master's thesis of sorts, but not even thesis. It looks like a paper. But let's take a look at it, right? So let's move that over here as well. Move downloads 093 here. Okay, I'm gonna open this one up in Zernal and just read the abstract and see if I can understand it. And if I can't, then we'll go from there. So let's do Zernal pp 09 whatever, and move this down here so I can still read chat. Scroll in, up. Okay. Today the subject of fractal image compression continues to remain perspective. It is connected with the fact that the ideas about self-similitude of the world put in this by Mandelbrot technology have huge potential. On the other hand, the difficult mathematical apparatus, which is the cornerstone of this area of knowledge, does not provide concrete computing procedures for the realization, and it provides the huge field for carrying out researches. That was a tough read. I'm gonna hold my judgment. I do realize that, like, look, there's a lot of non-English speakers who regularly write papers, and, like, there's nothing wrong with non-English speakers. I'm just saying that, like, I'm now interested to see what journal that was published in. Ocular 09 here. That's just tools. How do I select again? Setting, tools. I can't just select. How do I select? Settings, tools, text selection. Okay, let's go over here, open this up, paste here. This is published in, where is it published? International Journal of Electrical Engineering, I believe. That's what that would stand for. No. I already have it. Let's Google that. International Journal of Electrical Engineering. No. Yes, this is it. International Journal. And now let's look if we can find the impact factor. Impact factor. And let's see what we got here. I realize, like, I shouldn't... This, Electrical Engineering and Technology is a different journal. International Journal of... You're telling me they have an impact factor in 2020 of 10? How do you have an impact factor of 10? That means every single paper that you're publishing gets 10 citations. To go from 0.43 in 2010 to 10 in 2020, I don't believe that. Especially when you have like 1995-esque, like graphics going on your site. They cite their own papers. No doubt they cite their own papers, but 10 citations per article. You're telling me that people publish a paper, publish 10 more of their papers and cite their own stuff. I just don't believe it. I mean, like, what is the impact factor of PRA? Impact factor of physical review letters, which is one of the premier, like, publication places for physics. Like, if you get a paper in PRL, it's a big deal. And I think their impact factor is 8, right? So to say that some random journal that I've never heard about has a higher impact factor than PRL is kind of unbelievable. Maybe it strikes me that, yeah. By the way, have you considered doing something on identifying questionable research publications? I was thinking maybe we should, actually. After looking at this, I think this would be a good idea. Someone earlier in stream had the question, or there was a discussion earlier in stream about basically a video or a topic on how to read research papers. And the more I think about it, I think maybe we should do that. And with the whole caveat that, there are probably methods that people know about that I don't know about, and certain fields are different. Like, for example, in areas of computer science, a lot of the conferences matter a lot more than the conferences in physics, right? So conference proceedings matter a lot in, like, for example, areas of computer graphics and stuff. But I would generally say that this is a good idea, and I think I should probably do it. In fact, maybe I just do that this weekend as well. I think that would benefit a lot of people. Like, not only just how to read a research paper, but how to tell whether a research paper is credible, right? How to see if a field is dying. How to yeah, okay, this is good. I think this is like the second or third request I've had just this stream, so I'm fairly confident this is something I should do. Maybe I'll switch topics tomorrow and Friday to specifically talk about, like, how to read research papers, and maybe forming a script around that, and collecting ideas from you guys about what the best way to do this is, because I'm convinced it's a good idea. Okay, let's do 5-year impact factor here. Whatever, it doesn't matter, who cares? Impact factor doesn't matter too much, right? It's just something that you kind of want to look at if you're afraid that people are, like, if you're afraid that a paper is not genuine, you look at the journal it's published in, and that's the number one thing to do. I had someone send me something medical related recently, and the paper was absurdly unprofessional. Excel screenshots instead of tables, and funny stuff like Fourier analysis of sine waves. Well, I mean, like, how else do you look at sine waves? Fourier analysis is the number one way to do it, right? Like, how else do you do it? But a Fourier analysis of a sine wave is just a single point. Like, you don't really have to do much Fourier analysis on that one. It's fair enough, though. Okay, let's go here, there. I'm interested to see what the highly influential citation is here. Let's look at algorithm for fast fractal image compression, and let's go to Google Scholar and look that up. Again, I'm kind of just looking for papers right now. Go here, and I'm gonna look at the forward citations there. And they say one of them was influential, which is this guy, a review of fractal image coding literature, 1999. There we go. I love Notion though. Applying heavy mathematics on simple objects just because you can. It was supposed to be supporting research for a medical project. They also included an entire full-page trigonometry table. Okay, so the thing is, I don't know the medical field, right? Like, I do know when I was studying pre-medical physics, like the medical physics papers were phenomenally different than the physics papers, right? And a lot of times I found people like reiterating topics that were like freshman physics, and it was interesting, you know? But at the same time, I feel like if you're saying Fourier analysis of sine waves, I kind of feel like maybe you're not in that group, you know? Anyway, review of fractal image compression coding literature. I feel like this is another one that we might want to just have saved. It's in an IEEE journal, which you can typically trust. And let's just see what it looks like. Yeah, this one looks tame and safe, and I would generally accept this one. Ethically bankrupt for sure, but at least it has a trig table. Yeah. All right, let's move this over here as well. So I'm just going to Control C from here, and we're going to move downloads, what was 08, I believe? Yeah, over here. Okay, so we've got a bunch of papers, literally too many papers. And I think, again, this is something I don't really want to do the reading on stream so much, because this whole stream has just been reading papers. But we have enough that we can kind of look at, and I'm just going to parse through it and see what I can find. Funnily enough, I looked up the institute the authors were from, and there was a forum thread calling them morally bankrupt. No. I had to push up. I just... So my advisor, my PhD advisor, published a paper in, I think it was PRL, but it might have been another related journal, where he basically said that in certain circumstances, a Bose-Einstein condensate can act as if it has negative mass, as in, if gravity is going down, it will go up, right? Like, it's one of those things that was weird, only existed in a certain system, and that was it. Man, there were people that just rallied behind this. Not too many people, but enough that it got kind of concerning, where they were like, oh, there's no way this could happen, you're a crackpot scientist, or other people that were like, oh, thank goodness you found negative mass. You know, now all of my theories about how the world is actually upside down, like, now completely, like, it tracks, it works. And I'm like, look, what are you talking about? I don't understand. Like, this paper was literally for a very specific set of circumstances that you can't replicate anywhere else. I don't know. It was just really funny seeing the crackpots come to town on that one. Cool. Okay, this is good. And the fact that this has 400 citations is actually kind of remarkable to me. Let me go back to, let me undo, go back, undo again. Ah, crap. I can't find it anymore. Let me search this up one more time. So we're gonna grab this, open this, go to Scholar, and paste that. And now we're gonna look at cited by 47, cited by 453. So what that says to me is that maybe we were looking at the citations for the wrong paper. Like, we were looking at one with only like 47 citations, but this guy has 400 and something citations, which says to me that maybe this is what we want to do. Like, this is the review paper that everyone cites. Now wormholes work. It was stuff like that though, you know. Image encoding device, image encoding method. Image encoding device, image encoding method. Oh, is a patent. Right. 2020, we have a lot from 2020 actually, relatively high number. Medical image compression scheme using number theoretic. Anytime you put number theoretic paper in a transform, you know I'm going to click. I mean, come on. That's just clickbait. You can't put number theoretic transforms in a paper and expect me not to click on that. The Riemann-Lebesgue integral of interval valued multifunctions near lossless image compression using parallel fractal texture identification. Now that's what I'm talking about. Elsevier. I was excited until I saw Elsevier. Anyway, okay, I'm looking at. Let me get some water here. Opti21, thank you so much for following. Really appreciate it. Was this cited by anybody? It was cited by 6. So, I mean, since it was published in 2020, 6 citations, that's pretty good. People are clearly into this. Yeah, I'm just a bit... I am a bit unsure about this paper. Yeah, I'm a bit unsure about this paper just because... I don't know, I'm just unsure about it. I don't know why. Gives me the... Okay, what do we have here? I don't know if I like this paper or not, honestly. I think see, near lossless image compression using parallel fractal texture identification. That's literally the same as fractal image compression, right? We're literally just doing fractal texture identification. That's what we're doing. So I'm okay with that part of it. It's just the fact that the images are like snowflakes and like just constant like re-zooming in of the Sierpinski triangle without the bottom to the Sierpinski triangle is weird in a way. But whatever, let's just download the PDF. Maybe it's actually better than I think it is. You know, don't judge a book by its cover type of thing. Yeah, I'll still take a look at it. Again, it's just kind of a bit, you know, like screenshots of, it's just a bit weird. I don't know if I trust it or not, but that's fine. That's fine. It's fine. It's fine. It's fine. Let's just move it over here. It's another paper to look at. What do we have? Something like that. Downloads. 1-S. Yep, that's it. Okay. I'll look at 1 or 2 more papers. What do we have here? Remove these guys. Anything else that looks interesting since 2020? I'm not seeing anything, so let's do 2017. Fractal image compression using upper bound on scaling parameter, near lossless image compression using parallel fractal texture, iris features via fractal functions for authentication protocols. It actually looks like it's relatively active. Like the field is more active than I thought it was, which is good. Actually, it means that people are still interested in it. It's worth talking about, I think. Fastbar's fractal image compression on PLOS for some reason. I was not expecting something on PLOS. Application of image compression on agricultural image data analysis, fractal image compression using quantum search algorithm. I just feel like, okay, I think maybe I'm barking up a tree that might be a bit, you know, just a bit crackpotty. When you put fractals next to quantum, it really makes me feel like this is a crackpot field, which is unfortunate. But I think it's still probably fine. Like, it's still probably fine. Let's just go ahead and read through the review articles that we have. And I'm just going to go through, see if there's anything else here that seems interesting to, like, you know, image denoising using fractal hierarchical classification. This all seems good, you know? I'm happy with that. Okay, cool. I think, guys, this actually might be where I end stream for today. I've been streaming for about 2 hours and 30 minutes, but I just need to take a step back, read all the papers, and see what we need to do. So as a review of what we were talking about today, we're basically asking ourselves the question of how exactly do we know if we are attracted to, for example, the Sierpinski triangle or some other attractor, right? Like, it could be the Sierpinski triangle, it could be the Barnsley fern, we don't really know. So the question is, how do we uniquely identify that this iterative function system is that of the Sierpinski triangle? That was the overall question that we were trying to form. And the related question is, how do we find some sort of distance d, essentially this guy here, from a single point to where the Sierpinski triangle is? And so that was kind of the question that we were trying to solve. This brought us to a discussion on fractal compression, which we had already talked about on Sunday, and we delved deeper into the fractal compression literature, which is actually very fruitful. There's a lot of stuff there. So much stuff that, again, I think it's about time for me to stop reading papers on stream and just to read papers off of stream and try to figure it out there. So that I have kind of a good idea of where to go from there starting next stream. I'm hoping that by the end of the week, we can solve this question of, how to tell if you're attracted to the Sierpinski triangle or not. But also, I think you guys have convinced me that by the end of this week, maybe the question we should be asking isn't so much, maybe the first question, the first of our weekly videos for YouTube should be on how to read a paper. I think maybe that should be what it's on. And if we're talking about how to read a paper, in my mind, the things that we do need to talk about are, one, how to, so how to read a paper. So reading. But we also need to talk about, how to tell if a paper is legit, right? And, maybe talk a bit about journals, citations, etc., and this type of stuff. I think if we just have a general video talking about how to read the paper, how to look at citations, how to look at forward citations, all this kind of stuff, how to ask yourself whether this paper is actually a legitimate source or not, then talking in respect to that about journals, citation rates, and stuff like that, I think that in and of itself would be a good starting place for anybody that wants to maybe start reading papers for fun on the side. And I think that's actually something good to talk about that, I think we should definitely talk about. So I think you guys are right. I should make a video on that. So I think this weekend I'm actually going to do that. So next stream, I'm not sure if we're going to continue delving into fractal compression or if I'm going to spend time making the script on how to read a scientific paper. But certainly by next week, we'll be back to the question of how to tell if you're attracted to the Sierpinski triangle or not, because that's a very relevant question for the rest of this particular project, which is essentially an extension of fractal image compression onto kind of, in some sense, more general cases. And we're just going to see where it goes. So anyway, guys, that is it for today. Let's see who we want to raid at the end of stream. Let's do Lana. Lana's live. So let's raid Lana Lux at the end of stream. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys around next time for the next episode of Simuleos, where, again, we either talk about how to read a paper or we talk about fractal image compression one more time. Thanks again, guys, and I will see you around. Bye, guys.